All right, everybody, I've got the top of the hour. Let's go ahead and get things started off here. I'm Travis Walbeck. I want to welcome you to the NCAT from Research to Implementation webinar for July. Today's topic, we're going to talk about perpetual pavements using full depth hot mix asphalt, which is how we prefer to see it done. So we're glad that you guys have joined us here today. We're going to have Nathan Moore step in here in a few minutes, but Nathan's the assistant director for the test track research here at NCAT. He's responsible for overseeing all the test track research programs. Prior to his role, Nathan served as the lab engineer here for 8 years. He specialized in balanced mix design and pavement friction. He's got his bachelor's and his master's degree here from Auburn University, and he's licensed here in the state of Alabama. Dr. Suri Gadaganti is an assistant research professor here at NCAT with 8 years of experience in asphalt materials, pavement design, thermal modeling, and life cycle assessments. He earned his PhD from Auburn University in 2021. We liked him so much we kept him here. His research focuses on life cycle assessment, sustainability, and pavement materials and pavement design, and we're all really excited that he's a new homeowner trying to get that house wrapped up and ready to go. We also have our good friend Mike Skinner. He's the executive director for the Asphalt Pavement Alliance. He recently joined the APA after being the director of pavement engineering for the Colorado Asphalt Pavement Association, or CAPA. That's where I got to grow my friendship with Mike, was there. He is a professional engineer with 35 years of experience in the asphalt industry, building and promoting quality roads. So as we kind of click on how this normally goes, it'll be a little bit of an introduction. NCAT research is going to be covered by Suri. We'll talk about some of the things that we've done with the perpetual pavements. And he's going to dive deep into what that looks like. We're going to get the industry perspective from Mike. Any questions that you have, let's go ahead and have them in the chat box, and then we can address those at the end. We usually give you a few resources to help out, and we'll close things at that point. So the NCAT test track was originally constructed in the year 2000. And back in the late 90s, using the Darwin or the AASHTO 93 design guide, the pavement thickness came up to be 2 feet to build a perpetual pavement. And that's what the intent was here. So there was much of the test track was built really, really deep. So they ended up becoming perpetual pavements. And that's what the way we kind of define perpetual pavements here is that it's a long-lasting structural pavement with no need of major rehabilitation. So we should be able to handle the structural loading of the trucks essentially forever. We just need to do maintenance on the surface, mill and fill, pavement preservation techniques, whatever that needs to be to just take care of the surface. So a couple of ways we can do this. We can just build the pavement really thick. NCAT test track originally built 2 feet thick, 24 inches. Tremendous tonnage. That's one way to do it. Another way to do it is through, really high quality materials. Some of the polymer modification or the binder rich layers that we've been able to put in have helped us build some perpetual pavements. So again, there actually are 2 sections on the test track that are currently in service that have never been rebuilt. And so it's really fun for us to see and watch how those sections perform. So, the thickness, the original 2000, that's one way to do it. This here is a graph that essentially shows a 14-inch pavement, right? That's far thinner, but it was built with this binder-rich bottom layer. It was put in place, a couple intermediate layers there, and an SMA on the surface. This full-depth hot mix section has performed just as well. It was put in 2006. The strain gauges are in there that can gather all that data and watch and see how that performs. So we only see top-down cracking. It's the only kind of cracking we see in this kind of perpetual pavement, which really does our heart good because we know structurally it's performing well. We just need to take care of the weathering or the environmental distresses we would see at the surface. So given that, I want to turn the time over to Suri, and he can go ahead and show you some of his work that he's done with these full-depth HMA pavements, and we'll go from there.
Hey everybody, good morning. Again, my name is Suri. Thanks, Travis, for the great introduction and a really nice way to kick things off. The way I set my presentation is to give a bit background on what is a perpetual payment in general, but also mostly concentrating on what the research and findings and recommendations we got from the test track towards more implementation side of the story. A snippet of the evolution of payment thickness design in general in the United States pre 1950s, we were pretty much designing our payments based on experience. But then late 1950s came the Asher test, which basically formed the foundation for the empirical methods, what we are seeing, including the ASTO 1962 design methodology and also the 1993 design methodology, what many of the states as of now are still using, be we call that as ASTO 1993 or Darwin software. And early 1980s, with the NCHRP 126 project, we started looking at not just from the empirical standpoint, because empirical equations only could account for the materials used at the Asher test, and the climate, which is one location, which was in Illinois, and also the same subgrade material as part of the Asher test itself. The mechanistic empirical methods can actually, apart from the empirical or along with the empirical equations, it can also now take the mechanistic part of calculations in terms of stresses and strains into account. And 1990s, when the NCHRP 137 started, research on 137A started, which was taking most of the LTPP data sets to form what we currently call as MEPDG software, which was developed in or released in 2004. And many of the states are currently in the process of adopting it, and many states already did adopt MEPDG as their primary design tool. So that's all about the conventional payment, right? Conventional payment design. But what's happening in the perpetual payment design scenario, the perpetual payments were also kicking in the same time frame as the 2000s onwards, from help from Dr. Carl Monsmith's work and Dr. Thompson's work from UIUC, and from a lot of effort from Asphalt Payment Alliance and GAT Test Track. So I'm going to cover the perpetual payment aspect of the story. So as I said, majority of the empirical and ME approaches, which are the conventional flexible payment design methods, what we have, including the 93 and MEPTG, they rely on empirical and ME approaches. And the goal is basically, at the end of the day, is to optimize the thickness. The goal of the payment design is to find how many inches of asphalt layer, if my base is so and so, for this location, for this traffic, for these materials I have in my state. So what should be the thickness that I need to come up with? So that's the whole goal of the conventional design approaches. But the problem is we do not check for max thicknesses. As Travis said, with the experience of the original test track, we got 24 inches of asphalt concrete, 2 feet of asphalt concrete. That's looks like it's too much, right? So there is no check for a maximum thickness. So if you see this in a more of a graphical format, so this is an example. If you run the 1993 analysis or design with varying design easels, the equivalent single axle loads, because of the way the empirical equation work, because it's a mathematical equation at the end of the day that takes million easels as an input, it throws you out the keep on increased asphalt concrete layers, right? Like if you say 50 million easels, it will say, hey, you need to build an 18-inch asphalt concrete layer. That sounds really conventional, highly conservative because it's too thick. But the question is, how thick is thick enough, right? Do we have a control or a check, a way to cap off the thickness of the asphalt concrete layer so that beyond which, even though you're building your pavement thickness to be above that, there is no practical use of it. It's basically sitting and serving no purpose. And that is when we have the perpetual pavement concept. As just Travis said, the whole definition of perpetual pavements is basically, if we build our pavements either by thickness or by using high quality materials, that we control the structural distresses. And without any structural distresses, and if we can confine the distresses only to the surface, we don't have to go back and do a major rehabilitation, right? Like a complete reconstruction effort. if we can control that bottom of fatigue cracking, which is structural damage, and also the subgrade rutting, if we can control those two things and only limit the distresses to the top of the pavement right here, we can come periodically and just mill and fill that particular layer. So that way, we are basically saving a lot of material. So that's the whole concept of perpetual pavements, is to build that. And the original concept was proposed in United Kingdom, and then which was adopted by California, by Dr. Coleman Smith's team for I-710 project, and then adopted for one of the project in Denver. The whole philosophy of all these initial perpetual pavement projects, as Travis said, is have your surface layer as high quality rut resistant mix, and have your intermediate asphalt concrete layer a high modulus, high rut resistant asphalt concrete mix, and have a rich bottom layer which can resist the fatigue cracking, and build all these three different high quality materials on top of a strong foundation. So that way, you're basically not allowing much stresses to go to the subgrade, and basically you're protecting the subgrade that way. As I said, so this is a schematic that shows what we will be doing. So as I said, the perpetual pavement concept itself is controlling the bottom of fatigue cracking. And we know once we apply a load on top of an asphalt concrete pavement, because it's flexible, it generates that tensile stresses at the bottom of the AC. So our goal from the design perspective is to control that strain level to a certain value. So that way we are not having or initiating the bottom of fatigue cracking. And also to limit the strain on top of the subgrade that we are placing, basically by controlling stresses that are going on to the subgrade. So that way we are not seeing any structural rutting happening. Today's presentation, I'm going to primarily concentrate on the bottom of fatigue cracking, because structural rutting is not a driving force once we start designing these perpetual pavements to define the thickness. It's actually the bottom of fatigue cracking. And I'm going to spend most of my presentation time on the research that we did at NCAT Test Track regarding the bottom of fatigue cracking. So for some of you that knows a lot about asphalt mixture testing, if you see the bending beam testing, right? And the bending beam testing is basically a strain control test. And as we increase, as we decrease the strain level that we're applying on the beam, we start seeing increased life, right? Because once we start reducing the strain that we're putting on the beam, we are basically allowing that beam to sustain for longer time. And for any material, there is something called an endurance limit. Basically, if you are applying a strain value below that endurance limit, that material is gonna stay there for infinite life. Basically, what it does mean is if you're applying a strain level below that endurance limit, you're basically not causing any fatigue cracking or any fatigue damage of that material. And over the years, different researchers try to do if there is an endurance limit for asphalt. In steel, the endurance limit is a big concept. In 1972, Dr. Coleman Smith, with his research from UC Berkeley, they came up with a number 70 microstrain. If you're basically applying a strain less than 70 microstrain, that material is going to be perpetual, or that pavement is going to be perpetual. And that they use basically for I-710 project, which is that 70 micron. And in 2007, as part of the big NCHRP project that Dr. Ray Brown at NCAT led, which is a laboratory study where we were testing a bunch of beam fatigue testing, what we came up, what Dr. Ray Brown and his team were able to come up with was for unmodified binders, that strain criteria is not 70, it's basically 100 microstrain. And once you start looking mixes with modified binders, that endurance limit criteria is even higher, which is 250 micron. But all the other studies until that point, until 2007, were looking at one single strain criteria, right? But we do know we have our pavements are not going to experience one single load, one single temperature every day, right? Our temperature changes, thereby our modulus of the asphalt concrete layer changes. And out on real road, we have axial loads that vary. So there is no single strain value that these traffic loadings and climate effects are going to produce. It's going to be a distribution at the end of the day. So in 2009, as part of Dr. Richard Willis's PhD dissertation, we started looking at several test sections that were embedded with a tensile strain gauge at the bottom of the asphalt layer, and started looking at whether single uh, endurance limit is going to solve the issue. If you see the data here on the table from different test sections, there are some of the test sections that had field measured strains above the endurance limit, but still were perpetual. For example, N3, N4, and N9, they had about 70% strain values above the laboratory determined endurance limit. But still, they never saw bottom of fatigue cracking, even after 30 million or more than 30 million easel applications. So what they came up with is basically there is no single strain value that we can design our perpetual pavements with. It's a distribution. So if you see, x-axis is basically the tensile strain at the bottom of the AC layer that we were basically measuring at the NCAT test track using the strain gauges, and y-axis is basically showing the distribution, the cumulative distribution, and the sections you can see in the lessons, but all the sections that produced strain values lower than that dark dot a solid line, they never saw any fatigue cracking. But sections that had or experienced higher tensile strain values than that red solid line experience or were bottom of fatigue crack. So those two demarcating points helped us to come up with what is called the measured tensile strain criteria proposed by Dr. Richard Willis and Dr. Tim back in 2009, based on field measured strains. But when we start designing these pavements, right, for design purpose, we cannot have the field strain measured values. We need to depend on some kind of mechanistic calculation methodology, like an elastic layer theory, because at the design phase, you're not going to have a capability to embed pavements with strain gauges, like what we have at the NCAT test track. So we have to depend on a linear elastic layer theory kind of a concept to come up with or to design our pavements perpetually. So that laid the foundation for the 2015 study. 6 years later, Dr. Tran, what they did is basically they took those sections and saw what is the difference between the actual field measured strain values and per road predicted strain values, which is a elastic layer theory software. So they saw the difference, and all the time, the measured strain values are always higher than the predicted using the theoretical mechanistic calculations. So if you see the plot here, so the dotted line was what was originally proposed by Dr. Willis in 2009, but this criteria, if we were using the calculated strain values, that was not helping us to demarcate sections that failed with bottom of fatigue cracking with the section that did not fail with the bottom of fatigue cracking. So what Dr. Tran and his team in 2015 did was come up with or an updated strain criteria. So if some of you are using the per road software, the default threshold right now you're seeing today on the software is basically these values, what you're seeing on the rightmost side of the screen. So this is coming from the test track research in 2015. And the updated criteria was validated with the Perpetual Pavement Award winning test sections based on performance. So these are sections on real road, not on an accelerated testing facility like NCAT test track, but these are out on the actual interstate and US highways across the country. And Castro, Alfredo. So what they did is basically, so this dark solid line, what you're seeing is the criteria that was proposed in 2015 by NCAT, and all the test sections which won the APA Perpetual Award, which basically saw good life and with no deterioration or structural damage. were actually falling on the left side of that line, which is basically where they're supposed to if they are performing perpetually. So what they did in 2017 is basically validated that criteria that was given in 2015 using the actual test sections, actual sections out in field. But when they were simulating these trains, they did not use the actual axle loads that happen in a regular highway. They used the legal load limit with 22 kips single axle load. I'm going to come to that, why that is important to mention. If you see the NCAT axle load spectra, because it's an accelerated pavement facility, we have single axles. We have 1, 2, 3, 4, 5 single axles weighing at 20 to 22 kips load. And we have a tandem axle between 38 and 42, and we have a steering axle between 8 and 12. But if you see the typical rural interstate axle load spectra developed by late Dr. David Newcomb and Dr. Tim, if you see the NCAT test track loading, it's basically extreme, right? Because it's an accelerated loading facility and we want to apply more number of easels in a very short span of time. So it makes sense because the axle loads what we apply are very close to the legal load limit, the US legal load limits. And all the studies that you saw at the test track until this point, the 2009, 2015, 2017, were based on that high intense loading levels. And even the validation work that was done in 2017 was with the US legal load limit. But the actual question is, if I'm a designer, right, if I'm working for a DOT, if I don't use the legal load limit, if I want to use just my axle load limit from my WIM data for the state, would this criteria still hold true? So that was the question we wanted to answer in 2014 is, can the criteria that came from 2015 study, can it hold true if we apply the highway load spectra, which is much less intense than the NCAT test track or the US legal load limit? So we got 31 test sections with the help of LDOT from across the state. And we also have the coding information of all those test sections. So we know whether those sections had bottom of patty cracking. If you see the right side of the screen, we know whether there was a bottom of patty cracked section or it's a perpetual section. So we were able to get that from the coding information. So what we did is we did the same thing what Alfredo and his team did in 2017. Okay, even though these sections are on interstate or on the US highway, let me assume 100% of the time, I'm gonna just see that 22 kip single axle load, which is the extreme condition that that pavement can experience. When we use that to verify whether it's demarcating the sections that failed with bottom of patty cracking with the sections that did not fail with the bottom of patty cracking, it was holding true. So all the red dotted lines that you're seeing are the section, or the red data points that you're seeing are basically cracked sections. All the green sections that you see are uncracked sections, basically the perpetual sections. And of 31 different test sections were or the actual highway sections information. So the black line, which is the threshold from the 2015 study, was able to demarcate correctly the perpetual sections with lower strain levels than that, with bottom of fatigue crack sections, which is higher than that limit in all 31 cases. So that was good. But what if we start simulate those sections apart, not using that extreme condition of 100% of the time this pavement is going to experience only that single axle. But now I want to use my WIM data and simulate my actual highway load spectra. We did that too. So when we did that for interstate sections, we used the axle load spectra of the interstate, and when we out of those 31 sections, and when we use the US highway sections, we use legal load limit. The axle spectra from the highway US highways. So the dark dotted line, the dark solid line, what you're seeing here is the one from 2015 proposed, but it failed to demarcate or to identify the sections that actually failed with bottom of patty cracking. If I'm using that criteria from 2015, all of these sections are supposed to not crack. But four of those sections did crack. So what does that mean is, if you are using the legal load limit to simulate during the design, you could use the 2015 threshold limits, but if you're a designer and wanting to use your own highway load spectra, you cannot use that because that failed to demarcate. So that is why what we did is we proposed in the 2024 study a new threshold limit, a much lower threshold limit than the 2015 one, and verified with other test sections or other sections from LDOT's highway network. And it the new updated, the dotted line, what you're seeing, the black one up here, is able to correctly characterize the section that failed versus the section that did not fail with particular. So in the end, what is the thing that we were able to find from 2017 to 2024 is basically, if you're using legal load limit during your design process to simulate your traffic levels, you can still use please use the 2015 threshold values, which are basically default in per road software today. But if you decide to use the axle load spectra, basically from within the per road software, you have an option to select the default values for an interstate versus a major arterial versus a minor arterial. If you decided to use that axle load spectra rather than the worst case scenario, please use the newly proposed threshold limits, which are much lower. But how does this perpetual payment design concept help devotees that did not that they do not right now use the perpetual payment designs, right? What is the application of this concept from a regular conventional thickness process? If you remember this plot from the earlier slide, if you use the Ashton 93 with increased in traffic, you're gonna still basically keep the increase in thickness value recommended. But if we can cap off the thickness to a max thickness using the perpetual payment concept, we can actually save the state extra dollars for the thicknesses that they don't basically serve much of a purpose. Because at this thickness in this example of 12 to 13 inches, this pavement is never going to see any structural damages. It's going to only see damages in the surface layer. So we come back and mill and fill every 12 years or 15 years, depending on the state, but or a preservation activity. But building those extra 6 or 10 inches up here, it's basically we are losing money up there without proper uses or optimized uses of the material. So this perpetual design concept is very helpful to cap off thicknesses for a given state. And as an application, we did the very same thing for LDOT, where we came up with what are those max thicknesses. So LDOT right now uses ASHTO 1993, right? If the thickness obtained from the 93 is above, let's say, for example, we divided the whole state into 3 different zones, depending on the temperature, basically the climate. The southern zones are the ones with the hottest or high A temperatures, and the north one, zone 3, which is the northmost one, is where the temperatures are the coldest. So for example, and these changes for the given base moduli and subgrade moduli, let's say if LDOT is designing a pavement with 6 inches of granular base, which has a 25 KSI of modulus value and a 5 KSI of subgrade value, the max thickness what we propose to LDOT is 15.5 inches. So if LDOT is using ASHTO 1993 for that scenario of the pavement, if the thickness comes out to be 19 inches, they can just build 15.5 inches because this pavement is perpetual at this point, and that extra 3.5 inches or 4.5 inches is basically serving no purpose. So that's how the states can actually use this perpetual payment concept in their regular conventional design as a cap off criteria or as a max thickness criteria. What are the softwares out there for perpetual payment design? So Dr. Tim developed per road software, which is used for the high traffic level road payment design, perpetual design, which is embedded into Pave Express today. So you can use either per road or Pave Express. Basically, both of them serve the same purpose. But Dr. Tim also came up with another tool called Per Road Express. This is for low volume roads. Where once you, if you're trying to design low volume roads perpetually, we suggest using the Per Road Express software. And you can access the Per Road software and Per Road Express software from the QR code on the screen. In summary, the recommendations are if you're using a legal load limit, basically 100% of the time, that payment is going to see only the 22 kip single axle. Please use the threshold what you're seeing right in the middle from 2015 from Dr. Tran's study. But if you're trying to use the actual highway load spectra to simulate your pavement's traffic levels, please use the updated uh, threshold values for the bottom of cracking, limiting the bottom of cracking. And also, as I said, as we talked about, most of the pavement design thickness systems out there, including the 93 and sometimes MDPDG, do not check for maximum thicknesses. We do check for minimum thicknesses, but we never check for the maximum thicknesses. If we can adopt or combine the perpetual pavement concept with the conventional designs like the 93 and MEPDG, we could basically optimize the usage of resources by capping off the maximum thicknesses. And these are the references I use throughout the presentation. So if you're interested, please go and access those reports and papers. And with that, I'm going to hand it off to Mike.
Good morning, everybody. Thanks for joining us. Suri just shared a fantastic summary of how we got to where we are today with perpetual pavements and why they're important to the industry. I'm gonna take that to the next step. And our role at the Asphalt Pavement Alliance is then how do we take this message and turn it into deployable, actionable items for agencies and owners across the state. So let's just kind of go through that. Before we do that, I'll just share a couple little fun slides. So I live in Denver, and so I've been in the asphalt industry for 35 years. I spent the first 25 years of my career as a design consultant, as a consulting engineer, doing construction materials testing, mixed designs, forensic investigations, etc. And then, as Travis mentioned at the kickoff, I spent the last decade as the director of engineering for the Colorado Asphalt Pavement Association. I've stepped now into the role of the executive director for the Asphalt Pavement Alliance, but I like to show this picture. This is the $1 Million Highway, US 550 state highway here in Colorado. And into that picture is the little town of Ouray. On our side of the picture is the town of Durango. The $1 Million Highway is named that because it's one of our scenic byways in Colorado with $1 Million views. But it's quite taxing to drive down the road there because you'll notice there's no guardrail. This is Red Mountain Pass. It's beautiful, but if you get on the road behind a tourist that hasn't ever driven this before and they're pulling a fifth wheeler or something like that, they go very slow and it can be very challenging. So you're looking at this with these long drop-offs down to the river down there below, and you wonder, why are there no guardrails here for safety? Well, the answer is because Red Mountain Pass is the most active avalanche zone in Colorado. And so CDOT routinely comes through here and blasts for avalanche. They send charges up the hill, blast for avalanche, and just around the corner that you can't see in this photograph, they actually constructed an avalanche tunnel that they built it, and you actually drive through it because that avalanche chute was so prone to sliding multiple times a month during the winter. When US 550 closes, it's about a 240-mile detour to get around. You got to go all the way up and around through Telluride when this closes. So they work very diligently to maintain this. But for those of you of our friends who live in the southern states, this is pretty scary in the wintertime. Look at that, how slick that is, and there's no guardrail. It's interesting. But I do want to share another, just a highlight story of our industry and how we're successful. And this is the Glenwood Canyon. This is an 18-mile stretch of Interstate Highway I-70 through Colorado. Now, in 1956, when President Eisenhower signed the Interstate Highway Act into law, which authorized federal funding to complete the interstate highway system. At that time, I-70 dead ended in Denver. And if you wanted to continue to go west, you had to take the state highway US 40 to get out to Salt Lake City and move in that direction. So as I-70 was improved over the decades, the last piece remaining was this piece through Glenwood Canyon. That's the Colorado River down there on the bottom. That's Amtrak on the other side, and you can see the original alignment at the very bottom of the picture there. That was an interstate highway. It was one lane in each direction with no shoulders. It carried interstate level traffic, interstate level cargo, and bicyclists because it was the only way to get through the canyon without a shoulder. It was a nightmare to drive through there. So decades ago, it was scenic, but it was terrible to drive. So CDOT improved it, and the only way they could do that was they were bound by the river on one side and vertical canyon walls on the other. So they built this zigzagging, cross-elevated portion, and it's really the crown jewel of the interstate highway system that Colorado deals with. But it's not without its problem. Rockfall is a real issue in the canyon, and you can see the size of that rock with CDOT is standing on top of it. They're setting charges in there to blast it and crack it in half. But where I'm going with this picture is talks about our industry in terms of resilience and quick, speedy recovery from accidents like this. So this is another example, just like Red Mountain Pass, that if Glenwood Canyon closes, it's another 200-mile detour for all interstate highway traffic and cargo that has to detour up through northwest Colorado on small state highways. So speed of construction, speed of repair, and resilience is really a hallmark of our industry. But let's talk a little bit about how we promote our industry and how we engage with local agencies and DOTs across the country. And we do that through the Asphalt Pavement Alliance. Those of you who aren't familiar with the APA, it represents the three premier stakeholders of the industry: the Asphalt Institute, the National Asphalt Pavement Association, and the 40 or so different SAPAs that exist around the country. In addition to that, we have strategic partnerships with NCAT and other industry associations. But I like to have this discussion as we're talking about perpetual pavements, how we maintain our interstate highway system, the billions of dollars that are invested across the country. The blue lines there are the interstate highway system. The red lines are your state highway systems maintained by your DOTs. But the Asphalt Institute does a wonderful job of tracking the total number of lane miles that we have across the country that are surfaced with asphalt. We've all heard this term before. 94% of the roads in America are built with asphalt. Where does that number come from? It comes from this document right here. The Asphalt Institute summarizes reported data. Each DOT submits a summary of report to the FHWA that reports their lane miles and what it's surfaced with, concrete or asphalt. And then the Asphalt Institute takes that and puts that together and breaks it down state by state and comes up with an overall network. But that's why we excel as an industry. We're 94% of the industry. But how do we promote the industry, and specifically perpetual pavements? I'm going to get there in just a minute. But are we promoting it from commercial pavements? How do we promote and how do we leverage our brand and move forward? And perpetual pavements is a hallmark of the ability to do that. And I'll show you an example in a minute. Just last week, I happened to be over in Louisville, Kentucky for the Napa mid-year meeting. I took a little side trip. Those of you that are familiar with Kentucky, you'll know that's the home to the Bourbon Trail, which is the district. It's not an actual road, but it's a district between Louisville and Lexington with all the bourbon distilleries. So I was back there driving the beautiful roads, back roads of Kentucky, and I stopped and made a little video, put it on LinkedIn. I just said, listen, the Bourbon Trail, it's paved with asphalt. Look at these beautiful roads in the back roads of Kentucky. So those are some interesting ways that we promote the industry. But when we get to the topic of perpetual pavements, quality is truly the core of our industry. All of us exist to to promote quality in our industry. And our perpetual pavement awards demonstrate that perpetual pavements are not just cost effective, but they're built to last. And when we get into the cost effective element of perpetual pavement, that's a whole nother webinar. But the initial cost of construction savings to an industry can be very significant, that can either control the budget for a project, or at a set budget can extend it and add additional lane miles because of the perpetual concept. So this was a photo that Suri showed a little bit, and I like to talk about general rules of thumb, because when we're talking about promoting an industry across the country and across the nation, we can't get too specific. But when you fall into that realm of 11 to 14 inches, you start to talk about maximum thicknesses. And if you're doing your designs with optimized materials, high quality materials, whether it be the aggregates or the mixed design philosophy, balanced mixed design, or using polymers in different applications, you can live in that 11 to 14 inch range and have it become perpetual, which Travis and Suri have both commented on the fact that if we build it where we don't get structural cracking bottom up, and we only have to deal with surface cracking, which is significant where I live here in Colorado because of our extreme elevation, number one, and our freeze thaw cycles. But if we can keep our cracking in the surface lift, then it's a win-win for the agency. So, resources for you that are out there either doing design or considering this. We do see a little bit at the local agency level, and I'll talk about that in a minute. But for the DOT level, there are lots of great resources out there. And one of the places I would point you to start, take a look at, is the APA website. It's driveasphalt.org. And there's a whole section there on perpetual pavements and resources that are curated from synthesis of information that will also lead back to the resource library that's available from NCAT as one of our partners. And there's a plethora of information. The last thing I'll share with us about resources is here at the APA, we are actively developing a new ebook, which will be published. Road and Bridges Magazine is actually putting it together right now. And it will live online, and it'll be about 20 pages. So it'll be short, sweet, to the point. It will not be a design guide, but it'll be a synthesis of current activities for perpetual pavements within hyperlinks to all other resources that will become available. So look for that ebook to come out a little bit later this year when that gets finished and that gets published. But so let's talk about it from a marketing perspective. This could be your grandfather's pavement, and the selection of that photograph of that car graphic was intentional. That some of these roads could be demonstrating service life that have been in place for decades and decades and decades, almost 100 years. And I'm going to share an example with you of almost 100-year road here in just a minute. But the overachieving pavement that we recognize, and we like to recognize as a perpetual pavement awards, we've seen lots of nominations since 2001 when we developed this program to recognize perpetual pavements. And we've seen award nominations for roads that have come in that have been in service from 35 years to 75 years. The average age of the winners is 43 and a quarter years. So let's call it 43 years. What does this program look like? Well, it's a win-win for the country and for the DOTs across the country, because all of the states that are colored in there are states that have been recognized and have won perpetual pavements. The concept behind this is demonstrating that this concept isn't just work in the South or for the southern tier states where they have warm environments. It works across the country in all weather environments, in all material environments, in all subgrade environments. When you incorporate regional or state-specific design criteria, this concept works. And you can see by the map, so we're always encouraging the states that are still grayed out to submit their perpetual projects for consideration. So what does this awards program look like through the Asphalt Pavement Alliance? So typically it's a DOT will identify a segment of road. They might also do this in conjunction with help from their state asphalt pavement association, but they'll put together a submittal package and send it into the Asphalt Pavement Alliance. Now, once we collect all of these nominations, they're all submitted to NCAT for judging. And so there's a pretty rigorous set of criteria that NCAT reviews every nomination to determine whether this road as nominated meets the criteria, and I'll share the criteria with you in a minute, of a perpetual award. Then we get that list back from NCAT, and then we award the different winners. Now, there are 3 different categories under perpetual pavement. You can win by design, meaning it was originally constructed to be that. But when we go back decades and decades and decades, some of this philosophy did not exist back then. So there are 2 other categories that agencies can compete and be recognized as perpetual roads. It's either by conversion or by performance. If it's a conversion road, it means it's an existing road that has been in place, that has been overlaid, and it has given it enough structural capacity that there are no longer structural failures on the road, and it's just resurfacing. And then we see the same thing in performance. It's an existing road that's in place, that has been in place for a minimum of 35 years for performance, that with a set minimum distance between mill and overlay or surface treatments. One of the roads that I would like to highlight as a winner for the 2024 season is the New Mexico DOT. This is going to be their first perpetual award. And what's exciting about this is the New Mexico DOT submitted a section of Route 66. Now, why this becomes exciting is you don't have to be in our industry. You don't have to be in the road building industry to get excited. Everybody knows the Mother Road goes from Chicago to LA, passes through. It just so happens that this segment of original Route 6, where you can see the black pin location there, that's the segment that won. It's a 9-mile segment that it was constructed in 1928. This was before the stock market crash. This is before World War II, to put this in perspective. And so we're really promoting this winner. You'll see lots of promotion developed around it this year, because not only is it almost 100 years old, but it's in celebration with Route 66 is celebrating its 100th anniversary as the Mother Road, which kicks off in January of 2026. So it's a great story. So here's what that section looks like for the New Mexico DOT. Like I said, that stretch was built in 1928. It's been resurfaced. It's been milled and overlaid, and that's appropriate to maintain the road, but there's never been a structural failure on this road, and it's never received more than an additional 4 inches of material net. That's part of the criteria for winning. So this is what it looks like, kind of desolate, south of Albuquerque, but the New Mexico Department of Transportation is very excited about this, and they will be recognized with their award in front of their Transportation Commission next month at their meeting in Albuquerque. So what do these award programs look like? These are the obelisks that are created and distributed to the DOTs around the country, but they represent pavements that were designed and built with outstanding care and exceptional quality. I commented that you can win under the 3 different categories: by design, by conversion, or by performance. But here's the criteria. The road has to be a minimum of 35 years old. It has to have a minimum of at least 13 years on average between surface treatments, meaning mill and overlay or minor rehabilitation. I'm not talking about crack sealing or things like that, but minor rehabilitation. You can't do it has to be a minimum of 13 years between mill and overlays, and you can't have any more than a 4-inch net increase to your roadway. If you meet those criteria, you can submit your nomination, and NCAT will then judge it and look at the historical performance data on the road to be eligible for a perpetual pavement award. So with that, Travis, I'm going to turn it back over to you as a moderator. I see that we have some questions, but that's an industry perspective of what I wanted to share about when you take the technical side of a design and how we can incorporate that for DOTs across the country successfully, accelerating initial speed of construction and long-term performance. Perpetual pavements have been in existence. We didn't call them that originally, but they've been serving our country for almost a century. So with that, I'll turn it back over to you, Travis.
All right. So can you guys hear me well? Sorry, thumbs up. Very good. All right. Yeah. So just in closing, historical structural calculation methods, they recommended very thick pavements to be perpetual. And Surrey talked a lot about that, and Travis mentioned that at the beginning. But what I like about perpetual pavements is really it rewards high quality materials. You can get perpetual pavements just by making a really thick mix, a thick pavement cross section. But having high quality base and subgrade and binder and mix will help you get there with lower thicknesses. And both Surrey and Mike talked about that. Perpetual pavement concepts, these are proven concepts, and they can be used to generate maximum pavement thicknesses over a very wide range of conditions. So in the work that Surrey talked about, where you've got different climate zones and different materials, and then Mike even made the statement about how you can build one of these things in any climate, any traffic condition. I mean, any load spectra, using a wide range of materials. A lot of these tools, they're already proven and they work. And then applying them, the conventional tools that we have to the perpetual pavement concepts can help us get there. So with that, I do want to thank Mike and Surrey for their excellent work, and we'll now go over some questions. Surrey, you've already been answering quite a few of these, but I was wondering if maybe you would take the time to go through and maybe answer them maybe a little more generally for the whole group.
Yeah. So we got a few questions on the chat box right here on the Q&A. So I'm going to read the question and I'll try to answer it from my understanding. So he's basically, what was the the subgrade condition for the AC thickness versus ACL graph shown on the presentation? 1993 design is extremely sensitive to subgrade modulus. You may get the that thick AC design for a very weak subgrade, not much for a decent subgrade. Thanks for the question, Evan. As I mentioned in the chat box, but for everybody, it's basically, so that particular graph is coming from an example analysis Dr. David Tim did to show basically the downside of the conventional design methods, because these are equations mathematically solved at the end of the day. They don't basically have a high cap. So coming to your point of like exactly what subgrade modulus was used for that analysis, to be honest with you, the answer is probably I don't know, but I try to do my the analysis with my Excel tool, what I have for the 93. If I was using a 5,000 psi subgrade modulus, I was getting basically for 100 million ASOs, the extreme condition about that 20-inch thick AC layer over a 10-inch base. If I'm assuming 0.44 structural coefficient for the AC and 0.12 for the base course, basically. I hope that answered the question.
Yep.
And sorry,
Yep.
Nathan,
No, yeah, keep going.
sure. All right. The next question was, how do the recommended maximum thicknesses for L dot align with the 2015 NCAT report? Higher or lower or about the same? So again, Evan, thank you for the question. So Evan was talking basically about the 2015 study, what I was showing here. So at the end of the study, what Dr. Tran, Dr. Tim, and the team did was they took 3 different climate zones, basically, with 3 different binder grades, Phoenix, Baltimore, and Minneapolis, and change the subgrade and base moduli and thicknesses and try to basically do a recommended maximum thicknesses for those climate zones. And unfortunately, L dot climate zone doesn't fall in that any of those 3. But if I had to take a closer one, which is Phoenix, probably right now, the new L dot max thicknesses, what we were coming up with are about 0.5 inch higher in thickness, or about the same for some of the conditions of base and subgrade moduli. So if it's too small moduli values or too softer moduli values for the underground underlying layers, we are seeing about 0.5 inch higher thicknesses for the L dot case. But if those are stiffer material, the base and subgrade, the foundation layers, we're basically seeing about the same values as were seeing back in 2015. I hope that answers the question.
Yeah.
I think
Thank you,
that's all.
Suri. And I
Yeah.
see that I see, sir, you've agreed to help Wasif out and send him some information. So that's really helpful. At this point, Mike, thank you so much for joining us today. I really appreciated sort of the history and just a national perspective of Perpetual Pavements. And Suri, as always, your work is excellent. So very well done. I do want to just steer the folks who are in this webinar. If you've got other questions related to the NCAT test track or training materials, you can visit our website at ncat.us, and there's all kinds of stuff you can find in there. Travis runs a great training program here at NCAT. So from short, sweet, kind of silly training videos like Training in Your Pocket to more substantial training courses, certification courses. I would highly recommend folks to look at that. At this point, I'll steer your attention to the next month's webinar. So save the date, August 21st, is third Thursday, as always, where we're going to be continuing the topic of perpetual pavements, but looking at alternative bases. So specifically cold central plant recycling and things like that. So with that, I want to thank everybody for your time this morning, and we look forward to seeing you next month. Thank you again to Mike and Suri. It was excellent.